Hello, this is a new lecture. We shall be speaking today about infinite series. And in our last lecture, it was concerning the Taylor expansion of functions. In other words, we found that some functions can be represented by series. And these series, we found that there are infinite series. And in order that the representation be valid, there were some conditions imposed on the series or on the function themselves in order to be represented in the form of a series. And in this lecture, the Taylor expansion is, as a matter of fact, is one way of representing series or representing function in the form of series. But there are other series and infinite ones that not necessarily be amenable to be represented in the form of a function that can be expanded in the form of these kind of series. And in these kind of infinite series that we shall be concerned in this lecture. Now, in this lecture, we shall focus on, first of all, the meaning of finite versus infinite. And then we shall be speaking first about numerical series, in other words, series that are represented in the form of numbers only. In other words, the elements of the series are numbers. And then we shall be speaking about a special kind of series that are called monotonic bounded series. And then we shall delve into the test of convergence. How do we know that our series converge? And then the alternating series, and these are date from the time of the 17th century. And finally, we shall be talking about power series. Now, the idea of what the meaning of finite versus infinite, usually series that have been dealt with in the ancient times are of the kind of finite series. In other words, the series has a finite number of terms. Why? Because the ancient nations, the Greek, for example, were afraid of dealing with such infinite series because they usually lead to contradictions. For example, for example, you aim at an object by an arrow, and this arrow hits the object, yet it traverses an infinite number of points. So how come the number of points are infinite, and yet it hits or it reaches the object? Again, one of the main or paradoxes that we have met, or the Greeks have met, is called the order contradiction, or the order paradox, in which they claim that you can change the sum of series by changing the order. It's like, for example, you have 1, then minus 1, and then 1, and minus 1 again, and you wish to add these up. To how you can, for example, write them in this way: 1 minus 1 plus 1 minus 1 plus etc. 1 minus 1, and these adds up to 0, of course. But you can also say it's 1 plus minus 1 plus 1, and plus minus 1 plus 1 again, and these cancel out to obtain 1. So how come the series becomes equal, the sum equal to 1 and 0 at the same time? So this leads to contradiction. The other very famous paradox, it's called Zeno paradox. It's about a tortoise and a racer, or a runner. Now you have the tortoise here, for example. It got a lead of the racer. For example, the racer starts here and the tortoise starts there, and it has a lead, for example, of 10 meters. Suppose it has a lead of 10 meters, then, and the racer, for example, has a speed which is 10 times that of the tortoise. Now, by the time the racer would have reached or completed 10 meters, the tortoise would have completed, for example, 1 meter. And then if he finishes 1 meter, then the tortoise would have done 0.1 meter, etc. And if the racer, for example, finished this 0.1, it would have been leading by 0.01, etc. So the racer would never attain or reach the tortoise. And this is again one of the paradoxes. All these they're not really paradoxes because they have a solution, and the solution is correct. And because the subject of convergence wasn't really being studied yet, it was only studied with the advent of the subject like calculus. So the series that the ancient nations dealt with are of this sort. The first one is called an arithmetic series, which is the sum of integers, of n integers, and the sum of which gives this right-hand side here. And you find this sort of arithmetic series associated with, for example, finding the area under the graph, and when the graph is a straight line, then you end up with a series of this source which you can calculate the area. And this one relates to the, again, you find it when you like to sum up, for example, the area under you have, for example, as we seen in the introduction lecture, that you can subdivide the base into segments, and then you construct a set of trapezoids or rectangles, and when you sum up these trapezoids or rectangles, then you have to resort to kind of series of this sort. And again, all these series, as you see, are all finite series. But again, you may find infinite series, and infinite series that were only studied well, as I said, with the advent of calculus. For example, the first one here is, for example, if we wish to represent the first one here, we can represent it by a Taylor expansion. We have here 1 plus x to the minus 1. If you want to represent it by Taylor, then first of all, the function f of x is equal to 1 over 1 plus x. Now f dash is equal to minus 1 over 1 plus x to the square. And f double dash, for example, is equal to 2 divided by 1 over x cubed, etc. And the Taylor expansion becomes equal to f of 0, which is 1. You do what is called Maclaurin series, which is the same as Taylor, except that you start from the point x equal to 0. So it is 1 plus x times the derivative at x equals 0, which is minus 1, plus x squared over factorial 2 times the second derivative at x equals 0, which is equal to 2, etc. So you get a series of this sort, 1 minus x plus x squared minus x cubed, etc. Now this series, of course, this series is convergent, provided there is a condition imposed on x. What is the condition? We said before in our last lecture, you have to investigate the remainder. Now the remainder after n terms, which is called Rn of x, is equal to what? Now it's equal to x to the power n plus 1 divided by factorial n plus 1 times the derivative, the n plus 1 derivative, and you can find it here. You can calculate it from here. You see here when this is 2, then you get here 2. When this is 3, you get 3 comes up here in the numerator, so you get factorial 3, etc. So in fact, you get factorial n plus 1, and because it changed, it alternates in sign. So what you have here minus 1 to the power n plus 1 divided by 1 plus zeta, because you said theta is a point between the point at which you expand, about which you expand your function, which is 0, and the point x, which you try to find the value of the function at this particular value, at the power n plus 1. Now, when you see your remainder here, this cancels out, and this remainder has to, when n tends to infinity, has to attenuate, or has to tend to 0. So if it tends to 0, then you say that your series is convergent. So here it tends to 0, provided that this tends to 0. Now, if modulus x is less than 1, so if it is raised to the power n plus 1, when n tends to infinity, then r of n tends to 0, and you see that your series converge. So this kind of series, this is an infinite series, the one that you said here, and it's infinite series which converge. So you could not actually study those kind of series except with the advent of calculus. And again here, this is a binomial expansion when the power is half, and you do the same thing and you arrive at the same condition of convergence. Here is ln 1 plus x, and ln 1 plus x, you don't need to do a Taylor expansion of it, because you can actually calculate it by integrating 1 over 1 plus x, and you get the same condition of conversion, except that it is said that when you integrate or differentiate, then you have to check the points, the endpoints. So at minus 1, yet it is not convergent. At plus 1, it is, because it's, as we shall see, it's called a conditional convergent series. Now, these kind of series, there is a condition imposed on them, but there are series to which there is no need to impose any condition. Like, for example, this one, e to the power x or sine x, that are convergent everywhere for all values of x. Now, to start to study these kind of infinite series, first of all, we shall deal with numerical series. In other words, series that contain only numbers, the elements of which are numbers only, and there is no such power series. In other words, there is no such function of x. Now, these kind of series how do we check the convergence of these series? One way mathematician thought about what, since we know the convergence, we have studied already the convergence of sequence, why don't we transform this series into a sequence? So the idea is to calculate something called the partial sum. In other words, here, for example, what you do, you have A1 plus A2 plus A3, etc. You call this one S1. And then the sum of the first two terms, you call it S2, and this you call it S3, etc. And now you do an analogy between your series and the sequence. If this sequence Sn, the sequence composed of the element Sn, which is a sequence, converges to a definite number L, then you say that the original series is convergent. And that's the way of doing it. Now the problem with this, the problem is solved if you can calculate Sn, but unfortunately this partial sum only is known for very few cases. For example, here is your Sn, this is your partial sum. So if this partial sum tends to a definite limit L, it means that your original series converges. But unfortunately, as I said, you only can tell or calculate Sn in a very few situations. For example, one of the known series, which is called geometric series, here it is. A is the first term and the ratio is R, and you get a series of this sort here. Now what is the value of S? Can you obtain a representation, an explicit representation of Sn? Yes, you can easily. You multiply this series by R and then you subtract both series to obtain Sn in this form. This is called the partial sum of an n number of terms of a geometric series in which the first element is A and the ratio is R. Now this series, sequence, because here now you have a sequence of partial sum. Now does this sequence tends to a definite value L? Yes, if this goes to 0, if Rn goes to 0. Now if modulus of R, because R could be positive or negative, is less than 1, then this Li tends to 0, and you got finally at the end that the sum of the series is equal to A divided by 1 minus R. So what actually you did here, what you did is that you transformed the series into a sequence and you looked for the partial sum and you try to study the limit of the partial sum. If the limit of the partial sum exists, then your original series really converges. And here the only condition on which we impose on the series in order, or on this partial sum of the sequence of partial sum in order to converge, is that modulus R is less than 1. But in most of the situations, unfortunately, we cannot obtain the sum of the series. Here, this is a very simple exercise in which we show how a number, like for example, this is a rational number because the digits keeps perpetuate all the time. So if you want to add up this series, then you can represent it in this form: 3 from 5 plus 17. It means the 17 repeats itself. So 17 divided by 1,000 plus 17, 10 to the divided by 10 to the power 5, etc. And this is a geometric series which converges because here you find directly that the ratio is equal to what? Is equal to 1 over 100. So if it is equal to 1 over 100, it means it's less than 1. So you can add it up, and you apply the result that we had in the last slide, which is the first term divided by 1 minus R, and you directly obtain the sum of your series. But usually, unfortunately, you cannot obtain the partial sum of series. So you have to resort to other ways of checking the convergence of those series. What you can do is that you try to study special kind of series. The most important of which, for example, are the monotonic, what they are called monotonic bounded series. So a monotonic bounded series, what the meaning of a monotonic bounded series? Now, a monotonic sequence, what we do is that we have to, of course, study sequence first, monotonic bounded sequence. Why? Because we said before that series, you can study them by transforming the series into a sequence of partial sum. So if you know the behavior of this sequence of partial sum, then you can reach a conclusion about the limit of your series. Now, a monotonic sequence is what? Is a sequence which is increasing all the time. It's like you're taking the lift, for example, when you want to go up, for example, a certain height, you take the lift, or you want to reach your flat. The lift always, it keeps always rising, and therefore it's called a monotonic sequence. Either it's increased all the time or decreased all the time. So if it is increased all the time, then you can tell this by finding that the element an plus 1 is always greater than the preceding element, whereas it is decreasing if each element is less than in value the element which precedes it. Now this is called a monotonic sequence. Now a bounded sequence is one where its elements do not exceed a certain bound. Of course, because you have to reach the flat. You cannot traverse the building. So this is called a bounded sequence. And since you are always rising all the time and you have an upper bound, which is the last flat, so you are bound to reach a certain level by which you cannot go far from it. So here it's called a bounded sequence, is one where its elements do not exceed a certain upper or lower bound. In other words, all the elements are bounded by a certain m, either from above or from below. Now, for example, this one is a monotonic increasing sequence, because when you start with n, this is a sequence. When you start with 1, you get 1 over 2. Then you take n is equal to, so 2 over 3. 2 over 3 is greater than 1 over 2. And then you have 3 over 4, which is greater, 4 over 5. So you just realize that this function, this sequence is monotonic increasing. But again, it cannot reach a value more than 1. Why? Because the numerator is less than the denominator. So it's always bounded by the value 1. So what it does, it kept the elements kept increasing until it reaches a certain level, L is equal to 1, and we call this level the upper bound of the sequence. Now, the set of real numbers, we said in our second lecture of when we talk about real numbers, we said that they have a property called completeness. The meaning of completeness is that any non-empty subset of R which has an upper bound, it must have a least upper bound. And this least upper bound, you can prove actually the convergence of this monotonic bounded sequence by what? We said before that all you have to do is that here, this is your L, which is your upper bound. And if you can find element of the sequence here, or an, same thing, that are greater, if whatever epsilon small, any neighborhood you take around epsilon, you always find element of the sequence. In other words, they accumulate, because we call this L here an accumulation point or a cluster point or a limit point. How would you know that? Is that you can, for example, take any integer n that depends on epsilon. And the more you take epsilon small, the more you decrease epsilon. Even whatever value of epsilon you take, if you can always find element of the sequence inside, they accumulate inside this neighborhood, then you can now realize, or you can conclude that this sequence converges. And in which case here you have an, and this is your upper bound here. If it's greater than L minus epsilon, for all n greater than an integer n, then your sequence converges because it's monotonic increasing all the time. And here you have this, this is the same equation here. In other words, the difference between your L, which is your least upper bound, your L, and minus an here, minus the element an, so long that you can always find in a deleted neighborhood of the number L, you always find by a radius epsilon, you always find element of the sequence, so long that you take n, the number of elements of the sequence, greater than some integer n, so long that you can always find some accumulation around L, then you can prove that the sequence converges. And in this monotonic sequence here, this L is the least upper bound, and n always the time is greater than L minus epsilon, and it accumulates in this small neighborhood, whatever the value of epsilon, irrespective of this value of epsilon. The more you decrease epsilon and the more you find an accumulation of the element of the sequence, then the sequence converges. So monotonic bounded sequence is a convergent sequence, whether it's monotonic increasing and bounded above or monotonic decreasing and bounded below, the sequence is always convergent. Now what we do if you want to investigate, for example, a sequence of this sort. Now the sequence here starts with the first sequence is 2. And then each sequence is called a recurrence relation. The sequence an plus 1 is equal to half an plus 6. Now here directly you notice something. You notice that each number an, each element an is greater than the one preceding it. Why? Because you add up 6 and you divide by 2. So it must be an plus 1 must be greater than an. But since you add up with 6 a number which is smaller than 6, it means that you never attain 6. So this is a sequence which is monotonic, increasing, and bounded above. So so from the theorem, it must be convergence. And here directly you have the second element is equal to 4. You add up 2 plus 6, 8 by 2, you get 4. The third element you got here 5, and the sequence increases all the time, but it's bounded above by 6. Therefore, the sequence is convergent. So here we study sequence without being interested in knowing an explicit form of Sn or of An. We can prove that the sequence converged based on our last theorem. Now, this is called a telescoping series. This telescoping series here, you can, it is a monotonic increasing sequence, of course, because you always add up. For example, the first term is 1 divided by 1 plus 2, which is 1 over 2. Then you have 1 divided by 2 multiplied by 3, etc. So this is a sequence which is always positive all the time. So it's monotonically increasing. To prove that it converges or that it complies with last theorem, you have to find an upper bound for the partial sum. Now here, we write 1 over n times n plus 1 in this form here, and then we realize something. We realize that they cancel out. In the brackets here, this is the first bracket, this is the second bracket, etc. You find that this cancels out with this one here. This term cancels out this term. In other words, the n partial sum is always bounded by 1 minus 1 over n plus 1 when you end up with the bracket number n, and it means that the partial sum is always less than 1. So if it is less than 1, but because it is monotonic increasing, so it means that this series converges. Whereas, for example, this is a harmonic series, and this harmonic series diverges. How do we know that? All you have to do is that you can, of course, it's monotonic increasing, but it's not bounded above. That's the problem. You have here, for example, S1 is equal to 1, S2 is equal to 1 plus half. Now, S4, for example, is equal to 1 plus half plus 1/3 plus 1 over 4. But 1/3 plus 1 over 4 is greater than half. So you get here S4 is equal to 1 plus twice half. So it's greater than S1. It's greater than 1 plus twice half. If you calculate S8, you will find, for example, you take the next 4 terms, you have S8 is greater than 1 plus 3 times half, etc. And you go on like this until you realize that in general S to of the element, the partial sum of the index or indexed as the number of S of the element number 2 to the power n is greater than 1 plus n times 1/2, and therefore it's always increased all the time. There is no upper bound for this partial sum, so we conclude that this series is divergent. Now here we come to a theorem which facilitates your test. Sometimes you don't need a test. Why? You find, for example, that the limit of an tends to 0. Now you have a series, and this series you want to know whether it converges or not. You have to add them up, but without adding the partial sum or adding the elements to obtain the partial sum, you just can check one condition. If this condition is violated, then you directly conclude that your series is divergent. And this condition is that the last term here, your an, if you found out that your element an tends to a different value L is not 0, then you conclude that it is divergent. And the proof is simple. You have an is the difference between 2 partial sums. And these 2 partial sums, you know that if the series is convergent, they must add up. They must go, each one must converge to the sum of the series. So this converges to S and this, or to L, you can call it L. This converges to L and this converges to L. So difference is 0. So it means that if this is a necessary condition for conversion, but it is not sufficient. In other words, if the limit of n and s tend to infinity tends to 0, it doesn't mean that the series is convergent. But the opposite is true. If this doesn't go to 0, that the series diverges. So this is a very simple test to check in order to check the divergence of the series, but not the conversion, because it's not sufficient. You may have that the limit tends to 0, and yet the series is divergent. Now, if you have, this is a simple theorem, if you have 2 series that are convergent, then of course the addition and the subtraction, and you multiply any series by C, then it's also convergent. For example, here, this one here is a telescopic series which is convergent. If you multiply it by 3, then it's also convergent. And the limit is equal to 1, so you multiply 3 by 1. Whereas this is a geometric series. And geometric series, you know that the sum is equal to the first term divided by 1 minus r. So again, you have here, so here it means that you have the sum of 2 series. Both of them are convergent, so it means that the sum of the series of partial series composed of the elements, of the sum of the elements from both series is also convergent. Now, when you add and subtract a finite number of terms, for example, here you have a series which is convergent, and for example, you cancel out the first 3 terms. Does this mean that the series is convergent? Of course, because this is already is convergent, and instead of you start from the first element, you can start from the fourth, for example. So since this is convergent and you subtract a finite number of terms, so of course the remaining series must be also convergent. In other words, you can always say that when you subtract two series from each other, if both are convergent, then the series, the difference is convergent, and especially when you subtract a finite number of terms, not necessarily even infinite number of terms. Now you have here a test of conversion. Now we've seen series that are, for example, monotonic, increasing, and bounded above, but they're not the only series that we can. This is not the only way to check the convergence of series. There are other tests of conversion. Well, the most important of all is called the integral test. This is a test which is very easily to be calculated. All you have to do, you have a series like 1 over n squared, and you wish to know whether it's convergent or not. You realize directly that 1 over n squared, you add up the area, because you have 1, then you have 1 over 4, etc. In other words, the sum of this series is equal to the sum of these small rectangles here. So what you do, if this sum exists, it means that since it is less than the area under the graph, it's bounded by the area under the graph, and it's monotonic increasing, then it must be convergent. So all you have to do is that you check the integral of 1 over x squared. If it exists, then it means that the series converges. And as a matter of fact, not only that, but you can also, since it can be greater than this series, look here, when you have 1 over 1 here, the integral here, this is the sum of this series are these rectangles which are greater than the area, which means simply that if the integral test converges, then the series converges, and vice versa, if so they converge or diverge together. This is a very simple test, for example, that you can do to check the convergence of series. Again, there is some comparison test. For example, if you want to check the convergence of this series, the element here, 1 over 2 to the power n plus 1, is less than 1 to the 2 power n. Now, this is a monotonic increasing and is bounded by the partial sum of 1 divided by 2 to the power n, which is here a convergent series, and we know that it's convergent because the ratio is less than 1. So since this is convergent, then the other one, the first one, is convergent. So if you have an an less than bn, and bn converges, it means that the series of having an element an converges, and vice versa. When bn diverges, then it means that the series sigma an diverges. So these are very simple tests. It's called the comparison test. There is another test also, which is called the limit comparison test. Here, the limit comparison test, all you have to do, you have two series with positive terms, and you can divide the element of an divided by the element of bn, the corresponding element of bn. If you take the limit as n tends to infinity, and you find that it tends to a number, it's equal to c, where c is positive and finite, then both series either converge or they both diverge. Here, as we see, we start to list some tests because we don't know the sum and we don't know the partial sum of this series. So what we do is that we rely on other ways of proving it, like, for example, being monotonic and bounded above, the comparison, for example, test. This is one of the tests, the integral test, which is very efficient, as a matter of fact. For example, here we have 3 examples. This one, for example, if you want to know whether this is convergent or not, it is convergent. Why? Because it's less than 1 over 2 over n squared. Of course, 2 gets outside the summation, so you get 1 over n squared. So this series, by comparison, this series is less than 1 over n squared, and the other one is convergent. So because 1 over n squared, as we said before, using the integral test converged, then this must also converge. Or you can use the comparison, the limit test. This one here is divergent. Why? Because when you integrate it, you get half ln n squared, and ln n, when n tends to infinity, you got infinity, so this diverges. This one also diverges because using the limit test, 2 over n, when you compare it to 1 over n is divergent, and you saw the harmonic series divergence, so this also diverges. Or you can use the integral test. Whereas this one is converges. Why? Because you can associate it with 1 over 2 to the power n. So these are examples to show you how you can manipulate or you exercise some one test or another. Sometimes you have what's called alternating series. In other words, series in which the elements keep alternating in sign, like this one. This is called Leibniz series, one of the earliest series of the 17th century that was investigated by Leibniz. And actually, it's Leibniz himself. He was a man of many aspects and many contributions. Like, for example, he investigated this series here, and he find a test on which one can check whether the series is convergent or not. So he said, what he said is that if the series is alternating in size, minus, plus, the elements are like this, then if your series attenuates, in other words, Bn plus 1 or An plus 1 is less than An, and the limit of Bn tends to 0, then you can conclude that this series converges. For example, here, this series, you have this one less than 1, this is, every element is less than the one preceding it, and the last term, of course, the term number n, when you take the limit when n tends to infinity, it goes to 0, then this series converges. To show this, actually, the proof is simple. Why? Because you start by B1, and then you subtract B2 to get S2. This is the partial sum of the first two elements. And then you add up B3 to get S3. And then you subtract B4. And you see how it is nested. And that's the idea of the partial sum of the convergence of the sequence. The sequence, when it accumulates about a point, it means that it converges around the same point. Here again, it goes like this. So the proof is simple. This is the sum of the first two terms, and this is the sum of the four terms, and you see that the series goes up like this, and it's monotonic increasing. But it is bounded. Why it is bounded? Because you can write the series in the form of B1 minus B2 minus B3, which is positive, minus B4 minus B5. So in fact, all of them are, you can, as if you are subtracting them from B1, it means that it's bounded by B1. So it's bounded by B1 in monotonic increasing, which means it is convergent. So this we call like this one. So this is convergent. This is the series of Leibniz is convergent. This is divergent. And the reason why this is divergent is very simple. You have to go back to the necessary condition of convergence. We said before that if your limit of An does not tend to 0, then it is divergent. And here, when you take the limit of this term here, the n term, you find that it tends to 3 over 4, and it perpetuates between minus 1 and plus 1. So 3 over 4 is not equal to 0. Therefore, this is by the simple test, it diverges. Whereas this one is converged. Why? Because it is a series which is alternating in sign, and at the same time it diminishes, or the elements are decreasing in value, so it must be converged. Now this one test that we can use directly to prove the convergence of series. We say that if you take the modulus of each term of the series to obtain another series called the series of absolute values, if this is convergent, then the original series must converge. And the proof is, for example, this one here. To check the convergence of this series, you take the absolute value, you get 1 over n squared, but sigma 1 over n squared is convergent. Therefore, this one is convergent, and this one too, because we saw that the cosine function is the range lies between minus 1 and 1, or that the modulus of cosine is less than 1, so this one is bounded by 1 over n squared, which is convergent, and therefore the series is convergent. Now, to prove this is simple. Why? Because this is your original series. You can take the modulus and you can represent this in the difference of these two series here. But this one is convergent from the definition. And this one is convergent too, because this series here, always modulus n is greater than n or equal to 0. So this one is always positive. So you have here, this one is positive, and it's less than twice modulus n, which is convergent. So this one is convergent. And if you subtract two convergent series, it becomes a series which is convergent, and therefore sigma an is convergent. And therefore, if you have a series, you are not sure about the convergence of the series, you take the modulus. If the modulus converges, then it means that the series converges. Sometimes the opposite is not true. In other words, sometimes the series, when you take the series with its signs, if it is convergent, yet when you take the absolute values, you find it divergent, you call this series conditionally convergent, like the series of Leibniz. If you take the modulus of this series, you find the harmonic series, and it's divergent. So we say that this is conditional convergence. In other words, when you take the modulus, you find it divergent. So whereas itself, it is convergent, so we call this conditionally convergent. Now, these are the most important tests, but there are some other tests, like the ratio tests, and this is so easy test, which you can use all the time, and this you can prove it by comparing it with the geometric series, because here the ratio is always L, so you can bound this by L, and this L, if it is less than 1, as if the ratio of the geometric series is 1. So this one is less than 1, is convergent. If it is 1, the test fails, and if it is greater than 1, because the ratio, if it is greater than 1, it means that it diverges. And this is one easy test that you can do. Now again, there is something called the root test. The root test is the same thing. It's exactly like the other one. They even both work or they fail. And the ratio test, the root test, the same thing. You have the square root of the element an when you take the modulus. The same results you have with the ratio tests. You may have also a kind of series that are called power series. Like here, the power series, we have, for example, the sigma. And these power series, they are not necessarily obtained from the Taylor expansions, not necessarily, but they are functions of x, like this one here. You have a summation. This is a series which is the sum of x minus 3 to the power n divided by n. And you wish to investigate this series. In other words, you wish to know whether you conclude whether it converges or not. So what you can do, the easiest way actually to deal with this series is to apply the ratio test. So the ratio test is very efficient in dealing with this kind of series. So what you do, and we said if the ratio test gives you a value less than 1, so it converges, greater than 1 it diverges, and if it's equal to 1, sometimes actually, many times it fails. So here, because there is a condition imposed on x from the test that we are going to exercise on this example, so it means that we are going to show the region in which this series converges. So what we have here, we apply the ratio test. You have here the element a n plus 1. What you do is that you choose the element n plus 1 here. You get x minus 3 to the power n plus 1 divided by n plus 1. And you divide it by an, the term an, which is the preceding term, which is x minus 3 to the power n divided by n. So you multiply. In other words, you invert the quotient here, and you get something like this. And you wish to test the limit of this quotient here when n tends to infinity. Now, the result of this is n divided by n plus 3 modulus x minus 3. Now, when you take the limit when n tends to infinity, this tends to 1. So you end up with modulus x minus 3. So in order that this series, according to the ratio test, to be convergent, one should have that the modulus of x minus 3 must be less than 1. And this is your result. If the modulus of x minus 3 is less than 1, it means that in other words, if x lies between 2 and 4, it means that your series is convergent. Whereas if it is outside this region of convergent, then it means that it is divergent. Now, the problem here, you have to test also the endpoints. For example, if you put here x is equal to 4, now you get what? You get 1 over n. This is divergent. But if you put here x is equal to 2, you get what? You get minus to the power n divided by n, which is a conditional convergent series, because this is a series of Leibniz which is convergent, yet 1 over n, which is the harmonic series, is divergent. So it means actually that your region of convergence is much wider than this one. In other words, it's less than 4 and it's greater or equal to 2. Now, we can actually now apply this to you remember in our last lesson, we dealt with many of the expansion of the Taylor expansion of some functions. One of them was ln 1 plus x, and we said before, you remember that we have to invert the inequality and so forth. And for this one, we wrote as the condition of conversion that x is less than or equal to 1 and greater than minus 1. Why is that? Because when you put x is equal to 1, you get 1 minus 1 over 2 plus 1 over 3, which is conversion, this is conditional conversion. And yet when you put x is equal to minus 1, you get minus 1, minus 1 half, minus 1 over 3, which is minus 1 plus half plus 1 over 3, which is the harmonic series and is divergent. And this is why the reason why we took into consideration that the value of x is equal to 1 also leads to a convergent series. Now you have, this is shows you that when you have a series of this sort, power series, you wish to know the convergence of the series, then you have to impose some condition on the x, and this region x, which is the interval on which the series is convergent. In other words, you may take any value of x here and sum up the series, and you come up at the end with a sum that is function of x. If you are outside the region of convergence, it means that you cannot take x here to be equal to a value greater than a plus r, which is the ratio of convergence, or less than a minus r. Whereas it is convergent in this here interval here. Now with this, in fact, we come up to the end of our lecture of infinite series, and here we exposed the idea of the partial sum of series in order to study, in order to be able to apply what our knowledge of the convergent of sequence. And then we said that there are situations all the time that we cannot obtain this partial sum, and therefore we have to resort to other tests of convergence, and we mentioned many of them. We listed the comparison test, the ratio tests. There are many of them which are efficient, and with this we come up to the end of the series, and I wish you good luck again in your study. And as I always remind you that all of these lectures, whether the preceding ones or whether the ones that we are going to deliver, are all uploaded to the platform of the Unituno University, Telematic University, and until we meet again, I wish you good luck. Thank you.